Welcome back to Channel 3.14 News. I'm Stella. Today we're going to be talking about lines on 3D objects and how they act differently than on 2D objects. Then we're going to be talking about some historical controversy throughout history involving 3D objects and lines. First, Dr. Dot in the lab is going to be explaining how lines on 2D surfaces work. Then Dr. Dot and a special guest are going to explain how those exact lines behave differently on 3D objects. Now to Dr. Dot.
Hi, I'm Dr. Dot. I'm here to teach you about lines today. If I connect these 2 points right here and put this in between them, it makes a line. And a line extends forever in 2 directions, this way and this way, which means that it can't just turn around and intersect itself. So in Euclidean geometry, a line can never intersect itself. Now on to my second point. In Euclidean geometry, on any given surface, every line looks the same. This line is straight, and this line is also straight. Even though they go in different directions, they're both still straight and look the same. My third point is talking about parallel lines. Any line on a surface in Euclidean geometry, if you draw any other point, only one line can go through it that never intersects. So if I have a point right here, like that, only this line, positioned exactly like this, will be parallel to it. Because if I had one even slightly like this, eventually it would continue and intersect this line. In Euclidean geometry, 2 points connected create a unique line. For example, if I take these 2 points right here, only this line can go through both of them. Another line can't, and because there's only one of it, it's unique, just like you and me. On to my fifth and final point. In Euclidean geometry, all straight angles are congruent. A straight angle measures 180 degrees. This measures 180 degrees. So does this one. And because it's Euclidean and all straight angles are congruent, that means if I lay this on top of the other one, they're going to be the same. See? They're the same. There's no difference between the two of them. So that means that because they're both straight angles and they're congruent, it's going to be like that anywhere in Euclidean geometry, even if it's over here on the graph or over here. We're going to start off section 2 by introducing our everyday objects. Object A is a funnel, also known as a cone. Object B is a can of Goya black beans. No, we are not sponsored by Goya black beans. One claims that a line may never intersect itself. Well, I feel like proving that wrong. If I place this line here and pull it tight, it has to continue forever in either direction. That means that if it does, and I roll my cylinder like this, it's eventually going to intersect itself again. That, exactly, right here, proves statement 1 wrong. Shabuya, Euclid! Another example of this will be explained by Stella.
Hi, it's Stella from Down Under, coming through to you via broadcast. Now, on to Dr. Dot's first point. She was talking about how a line may never intersect itself when placed on a 3D object. Taking a sphere, this is another great example of how this can be proven false. Here you see a flat line laid on a sphere, and it is, in fact, intersecting itself, proving that first statement to be false on a sphere.
Statement 2 claims that on any given surface, all lines look the same extrinsically. While this might be true on a Euclidean surface, this definitely is not true on a non-Euclidean surface. First, I'm going to prove this using object A, a cone. So, if I start with my line at a certain point, and then I extend northeast in a straight line, then either way, eventually, it's going to intersect itself and make this shape, which we call the ribbon. So that's one way the line can look on the cone. The second way is if we just go straight north. So if we start like this and just go over, the line's going to look like this instead of like a ribbon. And those are definitely 2 different looking lines. I can also prove this statement wrong using the can of black Goya beans. Again, not sponsored. So if I take my straight line, just like on the other one, and I start at any point and I go just like this, it's going to create a circle like this, like we did with the other point statement. But so I can start like that, but if I start at a different point and go a different direction, it'll form a different shape, which we call a spiral. So the spiral can still extend in the same direction, in a different direction, and make a straight line, but it obviously looks different. That's a second example of how they look different. Statement 3 says that given a line and a point not on that line, there is exactly one non-intersecting line passing through that point. To demonstrate the truth of this on a cylinder, we're using object B. So, I've placed line 1, which is a straight line, across this, and I've taped it down so it won't move. This represents one line going one direction and not moving. Now, I've also drawn a point here to represent the point not on the line. So what I'm going to do is I'm going to take line 2 and I'm going to put it right through line 1. There's only one way to position this line so it doesn't intersect. Because even if I move it a tiny bit like that, eventually it's going to intersect with line 1. And then if I go like this, it's still going to intersect. So there's only one way for me to position this without it intersecting. That means that on a cylinder, there's only one line that can go through a point and not intersect the other line. Now Stella will prove this wrong using a sphere.
Secondly, a sphere doesn't have any parallel lines. So you have a line on a sphere. If you make any other point on this sphere and make a line out of it, it will intersect this line. Any other line you could possibly make will originally intersect the first line. Some people may think, well, if you have a line like this, why can't you just make a parallel line right here? But the thing is, as you can see with how poorly it's fitting the ball, that's not a true straight line.
It says that 2 points determine a unique line. This means that between any 2 points, only one line can be drawn. So, if between this point here and here only this line could be drawn, that would be true. However, if you take off this line and take this line and go from this point, then around the cylinder and back to the other point, that shows you that a second line can be drawn between the 2 points. So the points don't make one unique line. Stella will add to this in the terms of spheres.
Now to the point of 2 points determining a unique line. This is also proven not true on a sphere. If I make a dot here on this sphere, right there, and if I make another dot right here on the sphere, so you have 2 dots, one right there and one right there, I can connect these 2 dots together like so, creating only a line this long, or I can connect the 2 dots the other way around, starting at this dot, coming here, and ending at this dot, meaning that they create 2 non-unique lines.
It says that all straight angles are congruent. I'll be proving this false with my trusty object A. Taking my line, I dropped it! Oh my god, it's broken! I can't ever explain it. Do you think we can see if Dr. Stella can explain it in Australia?
Whoops, that's okay, Dr. Dot. Mistakes happen all the time. I made a makeshift cone out of this piece of paper. Now, I will tape the cone together. And you will see that a straight line, known as a parabola on a cone, runs through here and directly through here, creating a 180-degree angle, a straight line. But if you take the tape off, you will see that where I marked the straight line in pen, going from here to here, it is closer to 90 degrees. So by bending it, you turn this line from 90 degrees to 180 degrees, proving that not all straight lines are congruent. Now, if I wanted to, I could take more out of this piece of paper and create a cone out of that. For example, I'll use this triangle right here to create a cone by folding this over, like so. Now, when I create a cone, it'll still have a vertical line, but that vertical line will no longer be congruent to the line before. If I draw an approximate vertical line on the cone, and this is rough, so excuse any bends in the line, but if I draw an approximate vertical line on the cone, I'm not sure if you can see that, but my pencil is right here, and that goes to here. That creates a 180-degree angle, or straight line. But when you untape the cone, like so, you have an angle coming from here to here, which is definitely not an 180-degree angle. So if you can have a cone like this with a straight angle, and a cone like this with a straight angle, coming out of 2 different degrees, then not all straight angles are congruent.
Non-Euclidean geometry is also important in science. One example of this is the mapping of the moon. Scientists orbit satellites around the moon on a certain path and use collected data to map the surface of the moon. These maps can then be used when planning the placement and paths of rovers on the planet's surface. One example is the Lunar Reconnaissance Orbiter used in 2011. So, when mapping the satellite's path, the scientists need knowledge of non-Euclidean geometry because they need to know how straight lines act on a spherical surface. And then once the satellite maps around, they can use the data collected to figure out information on the moon's surface, like the distance between craters and the placement of rovers. And this way, we have extended knowledge of space, but we couldn't have done it without non-Euclidean geometry.